source directivity and location. We've looked at the case of an ideal or theoretical omnidirectional source of sound, which radiates evenly in all directions. Real sound sources, or sound sources that do not have spherical radiation, exhibit directional characteristics and therefore have varying sound pressure levels according to the angle of direction of the source. Examples of real sound sources include, of course, our voice, which I talked about earlier, loudspeakers, louvers and grills from air conditioning systems, or even open windows. It is therefore necessary to introduce the concept of directivity to calculate the sound pressure level at a distance from a source. What we can do is take the ideal omnidirectional sound propagation and apply a decibel correction for the directivity index. So the directivity index is defined as di is equal to 10 log Q in decibels, where Q is the ratio of sound intensity in a particular direction compared to the mean intensity over spherical radiation. Of course, if sound radiates equally in all directions, spherically, Q would equal 1. So if you substitute Q equals 1 into that equation for directivity index, the directivity index would be 0. If sound radiates with twice the intensity in a certain direction compared to other directions, then Q equals 2. And if you substitute Q equals 2 into that equation, the directivity index would be 3 dB. So you would have to make a correction of 3 dB over the case for omnidirectional or spherical radiation of that source. When we think about real noise sources, the directivity index is specific to that particular source. So it could be a loudspeaker, it could be a piece of plant like that on the right-hand side there, which is a chiller. It could be a car. Each of these different sound sources exhibits different directivity characteristics. It can also change with frequency. Typically, noise sources become more directional with increasing frequency. And this is because the sound wavelengths are very short at high frequencies. You might remember in an earlier section that the wavelengths at higher frequencies are in the orders of centimeters. Whereas at low frequencies, for example 63 Hertz, the wavelength is over 5 meters. So there's more directionality as the wavelength becomes smaller. In addition to the inherent directivity of the source, the location of the source can influence its directivity pattern. And in this case, on the right-hand side here with the picture of the chiller, it is sitting on a concrete platform or a concrete roof of a building. So this would exhibit different characteristics of directivity compared to if it was hanging in free space. We'll go into this further now. Let's look at a few different cases of the location of a sound source and how it affects its directivity. First of all, let's look at hemispherical radiation. Let's take that example of the chiller in the previous slide. If it was fixed on a hard roof, a concrete roof, the sound from that chiller can only radiate into a hemisphere volume. It is constrained by the concrete roof. Therefore, the same amount of energy is constrained to half the volume, and the energy density in the direction of propagation doubles. The additional hard reflecting surface increases the noise by 3 dB over that theoretical spherical radiation. So for example, if a noise source sat at the top of a mast and had a sound level of 70 decibels at 10 meters, if it was placed on a hard surface or a hard concrete roof, this sound level would increase to 73 dB at 10 meters. The next case is if a sound source is placed at the intersection between a wall and floor. In this situation, the radiation of sound is constrained to a quarter sphere. So the energy density doubles again compared to the hemispherical location, and another 3 dB increase would result. So overall, it's a 6 dB increase in sound level over the omnidirectional source. Or if you look at it in a different way, with the sound radiation restricted to radiate in a quarter sphere, if you input Q equals 4 into that equation for directivity index, DI equals 10 log 4, which is 6 dB. In the next situation, where we place a sound source in the corner of a room with two hard walls and the floor constraining radiation, the volume is constrained to 1/8 of a sphere. So all the energy has to radiate through 1/8 of a sphere of volume. Therefore, Q equals 8. If you substitute Q equals 8 into that equation for directivity index, the correction would be 9 dB. Now, a common example of this is the location of a subwoofer for a sound system in a domestic situation. The typical advice is to place the subwoofer in the corner of a room, and this is to provide increased bass or increased low frequency response from the subwoofer by using the hard reflective surfaces of the walls and the floor to create more intensity or more radiation of sound through a smaller volume.